Dear students, so in previous class we were discussed about the characterization property of an interval. Now we consider sequence of intervals. Consider an interval, let In, consider this interval, let In equals closed interval 0, 1 by n, where n is any natural number. Consider this interval. So here, what is I1? I1 equals closed interval 0, 1. Clear? What is I2? I2 equals closed interval 0, 1 by 2. What is I3? I3 is closed interval 0, 1 by 3, etc. Ik, what is Ik? Ik is 0, 1 by k, where k is a natural number. Means, consider this, suppose this is an interval, 0, 1, closed interval 0. This is closed interval 0. This is I1, which is I1. Then what is I2? I2 is closed interval 0, 1 by 2. This is I2. This is I2. I2. What is I3? I3 is 0, 1 by 2. Then there is 1 by 3. This is I3. I4, 0, 1 by 4 and so on. Surely, clearly, this I1 is a superset of I2. I1 is a superset of I2. Okay. Clear? This I2, what is I2? This is I2, this is I3. So I2 is a superset of I3. Clearly, I3 is a superset of I4, etc. Then, consider such sequences. Let In, the collection of all such intervals. The collection of all such intervals In, where n fall in n, having the property I1 superset, I2 superset, I3 superset, I4 superset, etc., such that In superset In plus 1 for all n fall in n. Then this sequence of intervals is called a sequence of nested intervals. That is called a sequence of nested intervals. This is important. Sequence of nested intervals. So what is sequence of nested interval? The collection of intervals In, where n fall in n, having the properties that I1 superset, I2 superset, etc., or In superset In plus 1. For all n fall in n, this property is called, or this types of intervals are called the sequence of nested intervals. Agree? Then, there's an important result. There's an important property that regarding this nested sequence, the property of the result is known as nested interval property. That's an important result. Nested interval property. What is nested interval property? So nested interval property states that consider a sequence, consider an interval. Let In equals closed interval An Bn, where n is a natural number. An Bn, where n is a natural number. Is a nested sequence of closed and bounded. This is the two crucial points. Closed and bounded. In equals closed interval An Bn for all n fall in n, being a closed bounded interval, nested sequence of closed bounded intervals. Then there exists a real number, theta fall in R, such that this theta fall in In for all n. This is nested interval property. In equals closed An Bn for all n fall in n, being a nested sequence of closed and bounded intervals. Then there exists a real number theta such that theta fall in In for all n fall in n. So this is a well-known result nested interval property. How to prove this one? So this proof is, what is In? In is a nested sequence. What is nested sequence? Since In is a nested sequence, then In supersets In plus 1 for all n fall in n. Agree? Then we have IN. What is IN? Closed interval AN, B. So what is I1? I1 equals closed interval A1, B. Okay. So clearly, this closed interval A1, B1 supersets closed interval A2, B2 supersets closed interval A3, B3 supersets, etc. Okay. So this can be rewritten from here. We have this is A1. So it is A1, B1 supersets A2, B2 supersets, etc. So clearly we have A1 less than or equals A2, less than or equals A3, less than or equals A4, less than or equals, etc., less than or equals AN, less than or equals, etc. Okay. Less than or equals, etc., less than or equals Bn, less than or equals, etc., less than or equals B3, less than or equals B2, less than or equals B1. Okay. So this sequence can be rewritten as in this way. So A1 less than or equals A2 less than or equals A3 less than or equals, etc. Finally B3 less than or equals B2 less than or equals B1. Okay. So this is closed interval A1 B1. So it is A2 B2, A3 B3, etc. This is A1 B1. Okay. So this is A2 B2. So this is A3 B3. A3 B3. This is A4 B4. So clearly A1 less than or equals A2 less than or equals A3 less than or equals, etc. B3 less than or equals B2 less than or equals B1. Clear? Okay. So now consider this sequence. Here that means here AN less than or equals B1 for all n falling A. AN less than or equals B1. So A1 less than or equals B1, A2 less than or equals B1, etc. AN less than or equals B1 for all n falling A. Agree? Now you define a setup. A equals set of all AN where n is a net. Define this set. Define A equals set of all AN for all n fallen n. Since AN less than or equals B1 for all n fallen n, then clearly what about this B1? B1 is an upper bound of this. B1 is an upper bound of A. Clear? Since there is an upper bound for this A, that means A is bounded above. A is bounded above. Then by the completeness property, this A has a supremum. A has a supremum. Okay. Let theta equals supremum of A. Let theta equals supremum of A. Then since theta equals supremum of A, theta with the least upper bound, that means AN less than or equals theta for all n falling n. Why? Because A is constructed as A equals set of all ANs for all n falling n. And theta with the supremum of A means least as it is the least upper bound. Therefore, AN less than or equals theta for all n fallen n. Okay. But AN less than or equals B1. Moreover, from here we can say that AN less than or equals Bn for all n fallen n also. Okay. AN less than or equals B1. AN less than or equals Bn. In particular, AN less than or equals B1. So AN less than or equals Bn for all n fallen n. AN less than or equals Bn means what about this Bn? Bn is an upper bound of A. Bn is an upper bound of A itself. Sure? Why? Because every element in A less than or equals this particular number Bn, clearly Bn is an upper bound of A. That means Bn is an upper bound of A, but theta is the least upper bound of A. Then by definition of theta, that means the least upper bound theta less than or equals Bn for all n fallen n. So it is theta less than or equals Bn and An less than or equals theta. So combines. That means this An less than or equals theta less than or equals Bn for all n fallen n. An less than or equals theta less than or equals beta means, so Bn means theta fallen closed interval An Bn. What is this closed interval a and bn? Which is nothing but in. Thus theta following in. So this is the nested interval property. If in is a sequence of nested intervals, then there exists a closed and bounded interval, then there exists a real number theta such that the theta should fall in where? This in itself. Agreed? So this is the well-known nested interval property. Clear? That's immediate. Why? Because the sequence this is a nested sequence. This can be rearranged as in this way. From here, we can it is clear that an less than or equals b1 for all n following n. Now we can construct such a equals set of all an for all n following n. Clearly b1 is an upper bound of this a. Why? Because every element in a is less than or equals this b1. Clearly b1 is an upper bound of a. Since a has an upper bound, a is bounded above by completeness property. A has a supremum, let it be theta. Since theta is the supremum of a, by definition of supremum, a less than or equals theta for all n following a. Again from here, it is clear that an less than or equals bn for all n following n. That means bn is nothing but an upper bound for this a, but theta is the least upper bound, so theta less than or equals bn. A less than equals theta less than equals bn combines, theta ranges from an to bn, that means theta fallen close to an bn, that is theta fallen I. So this is the requirement. Okay. Now there is another result that is related to this nested interval property. Here let in equals, consider another result. Let in equals closed interval a and b. In equals closed interval a and bn for all n following n. Be a nested sequence of closed and bounded intervals such that the length of in. What is length of in? Length of in. Length of in means it is bn minus a. Length of in means length of closed interval a and bn. The length of a closed interval is its upper limit minus upper term minus lower limit. So bn minus a. Okay, that satisfies, or it is such that infimum of this length of in, infimum of length of in, where n fallen n equals 0. Infimum of length of n, where n fallen n equals 0. Then theta fallen in is unique. Theta fallen in is unique. The uniqueness is our requirement. Theta fallen in. Why? Because since in is a nested sequence, closed bounded, nested sequence of closed bounded, or it's a nested sequence of closed and bounded intervals, then by nested interval property, theta fallen in. Now to show that this theta is unique. So how to prove that the theta is unique? By its proof is in this way. By nested interval property, there exists theta fallen r such that this theta fallen in for all n fallen n. Okay. Now for the uniqueness, if possible, there exists some eta fallen r. Eta is in a real number such that this theta also fallen in for all n fallen n. Now to show that this theta equals eta. Since theta fallen in is closed interval a and bn means an less than or equals theta less than or equals bn. Also eta fallen in means an less than or equals theta less than or equals bn. Okay, that means for all, this is true for every n fallen in. So this means for all n fallen in. This means modulus 0 less than or equals modulus of theta minus theta less than or equals modulus of bn minus a or an minus b. 0 less than or equals modulus of theta minus theta less than or equals bn minus an for all n fallen n. Clear? Okay. Now, but what about infimum? It is given infimum of length of in, that is length of in bn minus an for all n fallen n equals 0. Infimum of that one equals 0. So that means let epsilon is a positive quantity. Suppose epsilon is positive, then since the greatest lower bound of this Bn minus An is 0, clearly this epsilon is not a lower bound. Why? Because epsilon is a positive quantity. The greatest lower bound of this set is 0. Since epsilon is greater than 0, then this should imply epsilon is not a lower bound. Epsilon is not a lower bound means there exists some n following n such that Bn minus An strictly less than epsilon. Bn minus An strictly less than epsilon. So clearly, here 0 less than or equals modulus of theta minus theta less than or equals Bn minus An. Moreover, Bn minus An less than epsilon. So combinedly we have 0 less than or equals modulus of theta minus theta. It is strictly less than epsilon. Why? Because Bn minus An is strictly less than epsilon. Combines these two conditions. Then you have 0 less than or equals modulus of theta minus theta less than epsilon. Since epsilon being arbitrary, we have theta equals et. This is heavily depends upon the this condition, infimum of this theorem or this result hard only when infimum of the length of that interval is 0. Since its infimum means greatest lower bound is 0, you can choose an epsilon is positive. Since infimum is 0, no number greater than 0 is a lower bound, therefore epsilon is not a lower bound. Since epsilon is not a lower bound, there exists some n following n such that this Bn minus An less than epsilon. But then you can replace this Bn minus An by this epsilon. So it is finally 0 less than or equals modulus of theta minus theta less than epsilon. Since epsilon being arbitrary, the equality holds theta equals et. Okay. So this is an application, or this is a corollary of this nested interval property. That's there is imposing a condition, length of the given interval, the infimum of that length should be 0. This happens only when the condition holds. Agree? Okay.